This is lecture 8 of CS47. It's computer organization study. This is memory usage 2. So second part of the memory usage and storage usage that we'll be discussing. So last lecture, in lecture 7, we have discussed about internal storage of the processor, which is like register file, and we have seen how we can access, store information into those register file and retrieve them if necessary. This part is, and the next part, memory usage 2 and 3 put together, will be looking at the usage of the external memory, what we usually refer to as an RAM of your computing system. So we'll be talking about the memory usage with respect to MIPS processor, usage of the RAM with respect to MIPS processor. So as a model, like what we do here is to establish some common understanding and common convention that will follow for MIPS programming. So that's the memory model we want to establish before we proceed with how we can access memories from within assembly program. So if we recall, like this is our whole computing system with the control unit, ALU and register file being a part of the processor, but external to the processor there is a memory. It can be 4 gigabyte space, for example, for any 32-bit system, and it will be much more for 64-bit system. But we are going to look at with respect to a 32-bit processor because mainly we are taking MIPS as our base processor to drive our discussion. So this processor MIPS, since it is 32-bit system, it will support 32-bit address space, and which can support 4 gigabyte address space for a byte addressable memory. Now, what do we mean by this, like 4 gigabyte address space addressed by the processor? So processor to the processor, if you look at from the processor perspective, everything is a memory. Okay, everything is a memory to it, and what it always assume that per address it access 1 byte. Okay, per address access 1 byte. What does it mean? Like memory can return 32-bit together, it's a 4 byte information together upon requesting onto one address space. But the point is, from processor perspective, each address contains 1 byte. Okay, so processor perspective, a memory is a byte addressable device, so that it knows at the most granular level it can access a byte individually. Okay, so that's processor view of the memory system. On the other hand, memory can be complex and some special things around it. We'll look at that in next lecture. But for time being, let's also assume as a device, as electronic device, the memory connected to the processor is also a device which is byte addressable, means each address is basically point to one single byte of information. Okay, so that's our assumption. So if so, we have some usage guideline. Okay, so this is pure guideline, this is pure convention, software writing convention. It's not imposed by the hardware. For example, like convention says from this address 100800 till 7FFFFFC, we need to use it as a stack or dynamic data, like a heap data. And for example, 0 to the address before 0040 that is reserved, we cannot write there. But from hardware device perspective, nobody is restricting you to write anywhere in the memory, okay, at this level. So through assembly program, you can actually write anywhere in the whole memory space, okay. You can write, you can read, no problem. The processor will not complain at all, right? It's only the software convention that is enforced through compiler, operating system at some sort of like assembling level as well. It's purely a software convention and software concept. Okay, so hardware does not pose any restriction on accessing any part of the memory. It is only the software system around the hardware, like operating system, compiler, and to some extent assembler as well, imposes these rules to your software program. Okay, assembler is less restrictive. You can do much more things with the assembler. Sometimes if some assembler puts some special check, it may complain, hey, don't write into the text part because it's program area, and don't write into the reserve. But if you have an assembler which does not pose that restriction, then you are free to write and read into any part of the memory. Okay, so the division we are seeing here is purely software convention. Okay, purely software convention. So the convention says that we subdivide the whole memory space into couple of sections. Okay, and each section has its own purpose. For example, like from address 0040 0000, from that address till before 100 0000, till that address, our program, machine code of the program will be loaded in this area. Okay, in this space, and we call it a text. Okay, remember, like in the assembly program we do a dot text. So that's kind of corresponds to this part of the memory, means whatever we are writing after the dot text, our assembler mnemonics and instructions, they will be translated into machine code, and when we start executing them, that program will be loaded into the text part of the memory. It won't be loaded in the static data or stack or dynamic part. It will be there, and it will be starting from this specific address 00400000. That's why for the MIPS and in the MARC system, you can observe that when you assemble, your program counter is initialized at always at this specific address, because that's where your first instruction is. So it will fetch from that and go to the next and next and next. So that's text part. And from the higher part above the text is the static data till it hits 10008000, that address. So that is static data, means all the constants and things you define in the as a data in your assembly program, the dot data section, that goes here, the static data. Okay, the rest upper part is basically your dynamic data. The dynamic data is like, and the stack, like both are dynamic in nature, but we should actually call it a heap and stack. Both are dynamic data. So heap is something like memory allocated as you do, like for example, new operation in your high level program. So it goes and see which part of this dynamic data area is free, and it allocates that many space to you, that many bytes to you through the new, so that you can create one storage for a variable, right? So that's the heap. Heap grows up, like from lower address to higher address. And there is another concept called stack. So don't mix up with the software stack like data structure stack. Its operation is similar to that, but it is not that data structure stack we are talking about. It's an area which by convention used as stack through push and pop kind of operation. Though push and pop is not part of native MIPS system, but we use the stack part, dynamic data stack part, in that fashion, and it grows downwards, mean from higher address to lower address. So if you push the first element, it goes to the highest, like 7FFF, FFFC, and then push another, it actually goes to the lower address and then goes to the lower address. So it kind of grows down, which is counterintuitive than what stack is in your mind from data structure study, which is always grows up, right? Stack is empty, then you push something, so stack is growing up. So inside hardware convention, by convention, stack operation makes the memory, the stack pointer, if you say, it's go down. And this stack pointer, the top of the stack, is always pointed by the register $SP. Okay. Now, the other part reserved is from 00 till it starts the text segment, that is a reserved. And by convention, we should not touch this. Why we need that? How is it used in computing system? That question will be answered in CS47 computer architecture study. That too almost towards the end of that study, this will be explained what is being this area is used for. The other part, you can say, since it has 32-bit address space, your address ranges, the values are all from all zeros to all F, right? But in this picture, what we are seeing here, our highest point of being able to access is 7FFF and FFFC, that part. So what happened to the rest of the memory, right, till 0FFFFF, right? So that part also reserved, but this time is for operating system. Okay, by convention that part is reserved, but for operating system. Next slide we'll see that in a minute. So we'll talk about this part, but before we go into the next slide, I want to tell one more thing, one more observation here, that you see the stack pointer goes to 7FFFFC, right? And let's say you are writing a word from that address. Okay. As I mentioned, from processor perspective, and we'll be for this lecture, we'll be always assume the memory is byte addressable space. Per byte addressable device means each address it holds 1 byte. Now think that at this address of the stack pointer $SP, you are writing a complete word. Let's say you are pushing a complete word into the stack. So, but one address contains 1 byte. So what will happen to the rest of the 3 bytes? So rest of the 3 bytes will be written from lower to higher address. So whenever you are actually writing a complete word into a target address, what you are essentially doing you are filling up 4 consecutive addresses, each address pointing to a byte, right? So you are at this configuration with stack pointer is pointing to a location 7FFF and you are writing a word to the memory, to that memory location pointed by stack pointer. What you are essentially doing, you are writing into like this FFFC and FFFD, FFFE and FFFF. So you are spanning your whole information from 7FFF, FFFC till 7FFF, FFFF. Okay, so that's one reason that when you power up the system, your stack pointer, instead of pointing to 7FFF, FFFF, it points to like 4 byte below to make sure you can actually push a complete word without stepping into the higher memory address, which we'll see in a minute is reserved for operating system kernel. Okay, so so that's the reason why your stack pointer is initialized 4 byte below your stack limit. Okay, and second thing I want to explain, whenever I say about a stack pointer pointing to 7FFF, FFFC, or like global pointer $GP is pointing to 100,800. What I really mean here by the pointing is that the content of the register stack pointer or GP is that value. Like stack pointer contains 7FFF, FFFC, so that we can refer to that address, use that value of the stack pointer to use an address to write into the memory. Or GP, for example, contains 10008000. We can use the value of the GP and take that as an address and write to it. Okay, so that's meant by pointing to certain address, means that register itself contains that value of that, means contains the address value. Okay, address value. Now next, let's look at Mars memory model.